NENOMATICA, where mathematics meets YouTube excellence. In this example, we will find the times when the heart rate is above 110 beats per minute. The model is y equals 15/8 t squared minus 30t plus 200. We want the values of time t, where y is greater than 110. Let's translate the question into an inequality. We set 15/8 t squared minus 30t plus 200 greater than 110. Subtract 110 from both sides to isolate 0 on the right. Now multiply every term by 8 to clear the fraction. We obtain 15t squared minus 240t plus 720 greater than 0. To build intuition, let's look at the graph. We'll graph y of t and the line y equals 110. The intersections with the line y equals 110 will be the boundary points. We expect 2 intersection points, and we will verify their exact values algebraically. Now, let's solve the quadratic inequality precisely. Compute the discriminant. Delta equals b squared minus 4ac. Here is 15, b is negative 240, and c is 720. That gives delta equals 57,600 minus 43,200, which is 14,400. So the roots are t equals 240 plus or minus the square root of 14,400, all over 2a, which is 30. The square root is 120, so the roots are t equals 4 and t equals 12. Since the coefficient of t squared is positive, the parabola opens upward. Therefore, the quadratic expression is positive outside the roots and negative between them. We want where y is greater than 110, which corresponds to the expression greater than 0. That is t less than 4 or t greater than 12. But time cannot be negative, so we restrict to t at least 0. The final solution is the union of 0 to 4 open and 12 to infinity open. Recap. We translated the question into a quadratic inequality, simplified to standard form, found the roots 4 and 12, and used the sign of the upward opening parabola to determine the intervals. With the physical constraint time at least 0, our final answer is t in 0 to 4 union 12 to infinity. Example. We will determine all values of m so that the inequality open parenthesis m minus 3 close parenthesis x squared minus open parenthesis 2m plus 1 close parenthesis x plus m minus 1 is less than 0 holds for every real x. Intuitively, that means the entire parabola sits below the x-axis for all x. Let's build a quick picture. If a quadratic expression is always negative, its graph, a parabola, never crosses the x-axis and opens downward. We'll visualize this with a downward opening example that sits entirely below the x-axis. Now for the method. A quadratic x squared plus bx plus c is always negative for every real x if and only if 2 conditions hold. First, a is less than 0, so the parabola opens downward, and second, delta is less than 0, so there are no real x-intercepts. For our expression, identify coefficients. A equals m minus 3, b equals negative open parenthesis 2m plus 1 close parenthesis, and c equals m minus 1. We impose delta less than 0, b squared minus 4ac is less than 0. Substitute a, b, and c. Then expand and simplify carefully. We arrive at a single linear inequality in m. Next, solve each condition. From a less than 0, we get m minus 3 less than 0, so m is less than 3. From 20m minus 11 less than 0, we get m is less than 11 over 20. Let's write those as 2 sets and then intersect them. On a number line for m, the intersection of open interval negative infinity to 11 over 20 with open interval negative infinity to 3 is simply the smaller one, negative infinity to 11 over 20. So the solution set is all m less than 11 over 20. To build intuition, let's test 2 sample values. The solution set is all m less than 11 over 20. To build intuition, let's test 2 sample values of m on the graph. In this video, we will determine the range of the parameter m so that a quadratic expression is always positive. We will follow a clear, step-by-step approach that you can reuse on any similar problem. Here is the problem statement. We want a equals mx squared minus 2 times parentheses m minus 2 times x plus 1 to be strictly positive for all real x. We will encode that as a of x greater than 0 for all x. To guarantee a quadratic is always positive, we use two conditions. First, the leading coefficient must be positive, and second, the discriminant must be negative. Using the even b trick, we can use delta prime for convenience. For our expression, we read off the coefficients at equals m, b equals negative 2 times parentheses m minus 2, and c equals 1. Because b is even, we use the reduced discriminant. Delta prime equals b prime squared minus ac, where b prime equals b over 2. Now, we simplify delta prime. Square negative parentheses m minus 2 to get m squared minus 4m plus 4, and then subtract m. The negativity condition delta prime less than 0 becomes m squared minus 5m plus 4 less than 0. We solve the inequality by factoring and using a sign chart. Factor m squared minus 5m plus 4 as parentheses m minus 1 times parentheses m minus 4. The critical numbers are m equals 1 and m equals 4. Because the leading coefficient is positive, the product is negative between the roots, so the solution for this part is m in the open interval 1 to 4. The second condition for always positive is that it is greater than 0. In our case, it equals m, so m must be greater than 0. This gives a domain 2 of 0 to infinity. Finally, we intersect the two results. From the discriminant condition, we found domain 1 is the open interval 1 to 4. Intersecting with m greater than 0 leaves the same open interval 1 to 4. Therefore, the set of all m values is the open interval from 1 to 4. We begin with an example. Find the range of the parameter so that the quadratic expression a equals open parenthesis 5 minus a close parenthesis x squared plus 2 times open parenthesis a minus 1 close parenthesis x plus 2 minus 2a is always negative for all real x. For a quadratic in x to be strictly negative for every real x, two conditions must hold at the same time. 1. The leading coefficient is less than 0. 2. The discriminant is less than 0. Start with the leading coefficient condition. It is 5 minus a. We require 5 minus a to be less than 0, which gives a greater than 5. That is our first domain candidate, d1 equals the open interval 5 to plus infinity. Next, the discriminant condition. Using the reduced discriminant delta prime equals b over 2 squared minus a times c. With a equals 5 minus a, b equals 2 times a minus 1, and c equals 2 minus 2a, we get delta prime equals open parenthesis a minus 1 close parenthesis squared minus open parenthesis 5 minus a close parenthesis times open parenthesis 2 minus 2 a close parenthesis. Expanding carefully and combining like terms yields negative a squared plus 10 a minus 9 is less than 0. To understand the inequality in a, let us locate the roots of the equation negative a squared plus 10 a minus 9 equals 0. The sum of coefficients equals 0, so the roots are 1 and 9. Because the leading coefficient is negative, the parabola opens downward and is below the axis outside the roots. Therefore, delta prime less than 0 gives a less than 1 or a greater than 9. We write d2 equals open interval negative infinity to 1 close interval union open interval 9 to plus infinity. Finally, we take the intersection of the two domains. The first domain requires a greater than 5. The second requires a less than 1 or a greater than 9. The overlap is a greater than 9. That is the complete solution, and it guarantees the quadratic is negative for all real x. Recap. To make a quadratic negative for every real x, the leading coefficient must be negative and the discriminant must be negative. For our expression that gave a greater than 9. Try the mirror question next. Make the expression always positive. Welcome! In this example, we'll solve the inequality f of x equals open parenthesis x cubed minus 3x squared minus x plus 3 close parenthesis times open parenthesis x cubed minus 1 close parenthesis greater than 0. We'll label this as example. Here is the problem on screen. Step 1. Factor the expression. We will factor by grouping for the first cubic and use the difference of cubes identity for x cubed minus 1. Here's the rule box for grouping. And the difference of cubes identity a cubed minus b cubed equals open parenthesis a minus b close parenthesis times open parenthesis a squared plus ab plus b squared close parenthesis. Start with f of x equals open parenthesis x cubed minus 3x squared minus x plus 3 close parenthesis times open parenthesis x cubed minus 1 close parenthesis. Group the first factor. Bracket x squared times open parenthesis x minus 3 close parenthesis minus open parenthesis x minus 3 close parenthesis close bracket times open parenthesis x minus 1 close parenthesis times open parenthesis x squared plus x plus 1 close parenthesis. Factor fully to get f of x equals open parenthesis x minus 3 close parenthesis times open parenthesis x minus 1 close parenthesis squared times open parenthesis x plus 1 close parenthesis times open parenthesis x squared plus x plus 1 close parenthesis. Quick challenge. Can you predict what we will check next? Step 2. Analyze the quadratic factor x squared plus x plus 1. We compute the discriminant. The discriminant delta equals b squared minus 4ac. 4x squared plus x plus 1. Delta equals 1 squared minus 4 times 1 times 1, which is negative 3. Since it is positive and delta is less than 0, the quadratic x squared plus x plus 1 is positive for all real x. Step 3. Find the real zeros and multiplicities. From the factorization. The zeros are x equals negative 1, x equals 1, and x equals 3. Note that x equals 1 comes from the squared factor, so it is a repeated root of multiplicity 2. Repeated even multiplicity means the sign does not flip at x equals 1. Step 4. Draw a sign chart. We mark the critical points negative 1, 1, and 3 on a number line. From left to right, the signs are positive on negative infinity to negative 1, negative from negative 1 to 3, and positive again from 3 to infinity. Because x equals 1 is a repeated root, there is no sign flip there. Let's annotate no sign flip at x equals 1. Finally, since we want f of x to be strictly greater than 0, we take the positive intervals only and exclude the zeros. So the solution set is open parenthesis negative infinity comma negative 1 close parenthesis union open parenthesis 3 comma plus infinity close parenthesis. In this lesson, we will solve a polynomial inequality by sign analysis. Example. Given f of x equals left parenthesis 16 minus x squared right parenthesis times left parenthesis x squared plus 4 right parenthesis times left parenthesis x squared plus x plus 1 right parenthesis times left parenthesis x squared minus x minus 2 right parenthesis times left parenthesis x squared minus 4x plus 4 right parenthesis is less than or equal to 0. Our goal is to find all real x that satisfy the inequality. Step 1. Identify factors that are always positive. A quadratic ax squared plus bx plus c with a positive and a negative discriminant is strictly positive for all real x. Here, x squared plus 4 is greater than 0 for all real x, and x squared plus x plus 1 is also greater than 0 for all real x because their discriminants are negative and their leading coefficients are positive. These do not affect the sign, except they never make the expression negative. They only scale it by a positive number. Step 2. Simplify the inequality by keeping only the sign-changing factors and factor any perfect squares. Recall that x squared minus 4x plus 4 equals left parenthesis x minus 2 right parenthesis squared. So the inequality is equivalent for sign purposes to left parenthesis 16 minus x squared right parenthesis times left parenthesis x squared minus x minus 2 right parenthesis times left parenthesis x minus 2 right parenthesis squared is less than or equal to 0. Step 3. Find the real zeros and their multiplicities. 16 minus x squared factors as left parenthesis 4 minus x right parenthesis times left parenthesis x plus 4 right parenthesis, and x squared minus x minus 2 factors as left parenthesis x minus 2 right parenthesis times left parenthesis x plus 1 right parenthesis, together with left parenthesis x minus 2 right parenthesis squared. The total multiplicity at x equals 2 is 3. So the real zeros are x equals negative 4, negative 1, 2, and 4, with x equals 2 a triple root. Let us place these on a number line to prepare a sign analysis. Step 4. Sign analysis. We examine the sign of left parenthesis 4 minus x right parenthesis, left parenthesis x plus 4 right parenthesis, left parenthesis x minus 2 right parenthesis, and left parenthesis x plus 1 right parenthesis across the critical points -4, -1, 2, and 4. The squared factor does not change sign, but it does make x equals 2 a 0 of multiplicity 3, which is odd, so the sign flips as we pass through 2. Testing one point in each interval, we obtain negative on negative infinity to -4, positive on -4 to -1, negative on -1 to 2, positive on 2 to 4, and negative on 4 to infinity. Since the inequality is less than or equal to 0, we include the zeros as well. Therefore, the solution set is the union of intervals where the function is 0 or negative. D equals open negative infinity comma -4 closed, union closed -1 comma 2 closed, union closed 4 comma positive infinity open. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.